functional group here, the nitrile, or this group is also known as a cyanyl group, C triple bond N, that was put into this area of our discussion, but it didn't really look like the rest of the carboxylic acid derivatives. There's no carbonyl group, there's no CO double bond. So why are we actually even dealing with this nitrile when we're talking about these carboxylic acid derivatives? And it's because the chemistry of these nitriles actually parallels a lot of what we've just been discussing. And we can use hydrolysis here as a tool, structural tool, to help explain that. So if you were to take some generic nitrile shown here in the bottom and treat this under acidic conditions, you actually end up with a carboxylic acid. Or if you treat it with basic conditions, sodium hydroxide and water, you actually end up with, I'll put the sodium there, the carboxylate. So it's looking similar to some of the things that we've already seen. So let's look a little bit at what sort of a mechanism could we use to explain these observations. And that will hopefully help show why we're seeing these parallels. So under acidic conditions, we'll just use the letter R here. We've seen time and time again that under acidic conditions, we're going to protonate the carbonyl group in acids to make that carbon more electrophilic. We do not have that here. However, we have this cyanyl group, the lone pair of electrons on the nitrogen. So how about now instead, we'll actually protonate the nitrile. Having a positive formal charge now on the nitrogen. And then this is where we could draw a resonance structure where we move these electrons up onto this nitrogen and have a positive formal charge on the carbon. So this carbon is electrophilic now, just like the carbon of the carbonyl group. So now we could have water attack the carbon of the nitrile, so similar to the carbon of the carbonyl group of all the derivatives that we've been seeing, move these electrons onto this nitrogen. So that's one of the steps where they show we see parallel reactivity. So now let's see what we get as a next intermediate. I'm going to rotate the compound a bit to make it a little easier to see. And I put the C here because it's easier to see with the triple bond. Now we're going to end up with a double bond. So I'll get rid of the C standing for the carbon and just put it back in bond line structure. So we have a carbon that's going to be double bonded to a nitrogen and form a new bond with the oxygen of water. So let's put the nitrogen here, and there's a hydrogen attached to it. And then we have water at this spot. Okay, so this is looking a little bit more like our imine type species. Now we need to get to the carboxylic acid. So let's have a couple of proton transfer steps. So we have water around, it's going to take a proton off. So everything is the same except I took a proton off. And now we've generated hydronium. Need to get rid of that nitrogen in some way. There's a lone pair of electrons on the nitrogen. So in the presence of our acid, it could get protonated. I'll go down. I'm going to slide this up a bit. Everything here is the same, except now we have a positive formal charge on this nitrogen. And here, what we can do to help, I think, better show this is that we're going to end up taking off this proton here. So if we were to actually just take off this proton as it is, as in this structure, that should be quite energetically unfavorable. However, what's different here is we can actually draw an important resonance structure. So let's take, we have two lone pairs of electrons here. Let's draw a resonance structure. We're going to move these electrons here, these electrons out onto this nitrogen. And this was the importance of protonating that nitrogen. Make this a little bigger. So this is a resonance structure. which means that this oxygen here has positive formal charge on it. So that positive formal charge doesn't reside solely on the nitrogen, but it's actually distributed from the nitrogen, carbon, and the oxygen, which means this proton is going to be relatively acidic, because if we take it off the proton, we'll just have a neutral species. So let's go ahead and take that proton off. So we're going to have something like this. And now what we'll notice is that this actually is an amide. So normally we've been writing it like this. Just tilt it up a little bit differently. So in terms of the nitrile, we'll make this a little smaller so I can scroll up a bit. Here for the hydrolysis, the nitrile, in the presence of acid, becomes a carboxylic acid. So we're not there yet, but we have an amide. So we've taken the nitrile and we've converted it to an amide. However, we know that the amide can be hydrolyzed to the carboxylic acid. So we're about halfway there, but we won't draw the rest of the mechanism. But what I'll show is that normally I would have this on the board, so we're going to pretend that it's there. Our amide here, I'll come back to this in a second. But we saw with our amide under acidic conditions here, pointing to the middle, under acidic conditions, that's going to become a carboxylic acid. So that's what's going to happen next. As we would protonate the oxygen of the carbonyl group, water will attack a series of proton transfers that end up forming the carboxylic acid. So this is a long process. I'll scroll back down here. What ends up happening is our nitrile is first going to get converted to an amide, and then that's going to be converted to the carboxylic acid. So there's one little arrow here on the top going from the nitrile all the way to the carboxylic acid. Mechanistically is encompassing all of those steps. I don't know why it looks like the arrows didn't show up. Put the arrows there. So a long mechanism, but what's important here, well, there's several things that are important, but one important thing is to note that this nitrile, C triple bond N, shows reactivity like a carbonyl group, and that's, again, why we're discussing it here. So under acidic conditions, we can protonate it, and then have the nucleophile attack the carbon. So rather than C double bond O, it's C triple bond N, in this case, protonated. So if that's the reaction under acidic conditions, where we protonate the nitrile like we would protonate the carbonyl group, probably similar reactions to carbonyl chemistry under basic conditions. So let's see what happens there. And we'll only show part of the mechanism. How about under basic conditions? So now let's take our nitrile. We don't have acid, but we have hydroxide around. So we've seen hydroxide attack a carbonyl group here, like this amide or something like that. With a variety of reactions, let's have it attack this carbon. So this is where we see the parallel. And then let's collapse the C down to bond line structure. So we're going to have OH here. I'm going to move this up. We're going to have a highly energetically unfavorable species here. This nitrogen had a lone pair of electrons. It has a negative charge, so this is going to immediately get protonated. Forming this species. And now we're under basic conditions, so we're going to readily deprotonate this group. Let me put this down a little bit. I'll go over here. So now we have an O minus. plus water. And kind of like what we saw with the acidic conditions here now is that where in the acidic conditions we saw that the positive charge, I'll point to the top here, was delocalized by resonance, which allowed us to deprotonate this oxygen. This negative charge here doesn't reside solely on this oxygen, but we can actually also draw a resonance structure showing that it's delocalized. So let's move these electrons to resonance here and onto this nitrogen. And to help show this nitrogen had a lone pair, so in our resonance structure, oops, I forgot to move the electrons. So this resonance structure helps show that this nitrogen actually is quite basic, and so it will quite readily pick up a proton off of something like water. Forming this species plus hydroxide. And just like under the acidic conditions here, now what we formed again is an amide. So we've taken our nitrile, hydroxide attacks, protonate the intermediate, deprotonate now the hydroxyl group that was added, which forms this resonance structure, this hybrid that we saw here, which shows that this negative charge doesn't sit right on the oxygen, but actually also can reside on the nitrogen, which will get readily protonated. And now we have our amide. So just like with the acidic conditions, we're part of the way there. Actually, I should write it here. So we have multiple steps. I'll just put a bunch of arrows to end up in the end, in this case, having our carboxylate. So multiple steps. And I'll put it up here in the top too. Multiple steps to form the carboxylic acid. So these are lengthy mechanisms if one writes out the whole thing, but this would be the same here that we saw earlier with the amide. So the goal for showing these reaction mechanisms is that the nitrile here, C triple bond N, has reactivity that parallels that of the carboxylic acid derivatives that we've seen. There are some differences, but overall quite similar. So I'm pausing for a second to make sure we can have everything written down.